So welcome everybody to today's installment of the General Interest webinar series for Sharcnet. Today I'll be talking about how to understand and potentially reduce job wait times by examining the scheduler configuration, load in the queue, and account usage. And my name is James Desjardins, and I'm one of the HPC consultants at Sharcnet. So as an overview of what I'll be talking about and demonstrating today, I want to get across is the properties of the factors that affect wait times in the queue of the general purpose clusters, particularly your systems Graham and Cedar. And talk about usage decisions that can lead to unnecessarily long wait times in the queue. So there are several factors that affect wait times, but some of these are actually can be manipulated based on decisions about how a specific job is run. So understanding which of these decisions can be made can result in shorter wait times for the same throughput. And then one of the main goals today is really how do you query properties of the systems, the scheduler, and the job queue to understand what's happening on the system, how it's configured, what the properties of the schedule are, and what is the load on the system that's affecting the wait times. So there's three main categories we'll be talking about. The factors that affect the wait times, there's the resources in the cluster and the resource requests. So the resources that you're trying to run jobs on make up the cluster. These are the cores organized into nodes with memory and storage. And your jobs are resource requests. So what you're doing is you have a process that you want to run, and those require the resources. And the scheduler is the tool that's trying to distribute that work on these systems. The next thing is the order of jobs in the scheduling queue, or the priority. So the things that affect this are a target share. So all accounts that have access to these systems basically get a target share of the system. It's the amount of the system your usage at. And this is an important aspect of wait times, and we'll go over how to visualize this. So parts of that are the target share, and then your usage relative to that target share goes towards determining the priority of jobs that are submitted. And there's an important aspect of this called the core equivalent, and that is basically the amount of resources that are charged to a job based on things like the number of cores, but also the memory that's used by a job. And then finally, there's the scheduler configuration. So we have resources in the system that all of these jobs are trying to get access to. All of the jobs are submitted from accounts that have target shares and are being run based on fair access. But then there's actual scheduler configuration. This is how are the nodes organized? So all of the nodes on the system, how are they organized so that specific jobs get a chance to run and that specific resources are made available. And so specific resource requests are isolated to subsets of nodes for important reasons. And understanding how these subsets of nodes are organized can affect decisions on how jobs are submitted. So I want to talk at the end of today about the usage decisions that can lead to unnecessarily long wait times. And there's four very specific instances of this. So there's the node memory limits. And the memory requests at the edge of a certain type of node type can result in substantially longer wait times than are actually required for a job being submitted. And we'll go over why that's the case. Then we'll talk about the partition constraints. Certain types of job requests will get isolated to a substantially smaller subset of nodes than might be necessary. So it's important to understand where your job is ending up in terms of partitions. once we understand the distribution of partitions. Another issue that can result in long wait times unnecessarily is the fact that there are sometimes heterogeneous job submissions from a single account. So a user group might be submitting several different kinds of jobs, and this is typically the case. Now, the shape of a job can be either easy to allocate onto the resources or difficult to allocate onto the resources. For example, a very short runtime job on a single core with very small amount of memory can often fit in little gaps right away on the system. But a very large memory GPU job has very few resources relative to that, particularly if it's running for a long time. So these two types of jobs being submitted by the same account can have an effect on each other. And this can result in very long wait times unnecessarily for the difficult to schedule jobs. And then finally, we want to talk about the effects of core equivalent usage charge. This is understanding the way that jobs that run under your account are billed towards your fair usage of the system. So once we understand all of these properties and know the specific issues that we want to be able to address that can change the way that we submit jobs to reduce our wait times, we want to know, what can we look at on the system beyond the documentation on a wiki page, for example. So we'll look at querying properties of the system, the scheduler, and the job queue. So we want to know what resources are available, and for this on the system, we can use the sinfo or a summary by calling partition stats. We also want to know how the nodes are organized into partitions, and we can use the control show partitions command on the cluster. And then we want to understand the load on the queue, both queue jobs and running jobs on the nodes. And to do this, we can use the squeue command or sact command. Now, we can call these from the login node and then just look at the tabular data in the terminal. But what I want to do at the end of this is go over an example of redirecting this output to a CSV and then using tools on my local computer to really visualize and summarize the information. So we'll go over these commands in the terminal, and then we'll go over an example of using sact to generate a CSV file and then visualize it in Octave on my local computer. So just to get started with the content, we'll go over a bit of a review of things that we've talked about in other of these seminars about how the system is organized. So one of the first aspects that affects the job wait times is really the resources that are on the system and then the requests that we make for those resources. So this is an illustration of what a node looks like to me whenever I'm thinking about how jobs are scheduled. So the node is made up of resources. So it can be cores, and it can have memory, etc. Some of them have GPUs, a bunch of them have software licenses, and then these things are available over time. So what happens is these resources are available, and there's a scheduler that's looking at this node and all the other nodes in the system, and it goes through a scheduling cycle. So at this time, it checks to see what jobs are in the queue, and then it sees if it can submit those jobs. These are the parts of scheduling. Now, what we end up with, particularly in these large general purpose systems that are available to all researchers nationally, is we end up with a whole bunch of jobs in the queue, and all of these jobs have different sizes. So for general purpose systems, we have everything from small memory jobs that are serial on a single core for a short amount of time to large multi-node jobs that run for a long time. We also have GPU nodes, and we have separate very large memory nodes, et cetera, et cetera. Okay, so what we see in this figure is an illustration of what a node looks like in a way that we can then understand the shape that a job takes, or the footprint of a job takes on a node. And what we want to get across is that some jobs are more difficult to schedule and cost more at the end of the day that affect later priority of jobs. So if we have this basically simplified node where across here we have 10 cores, we have memory that can be shared across those cores, and then we have time going upwards in hours, we can see that jobs have different shapes whenever they're submitted. So the job size that we want to talk about in this case is just simplified to the number of cores and the amount of memory over time. So basically the job queue are all the jobs that are trying to run on the system. We have a simple 1 hour serial job that's requesting 1 gig, and that looks like this what we're seeing here. It's 1 core wide, it's 1 hour long, and it's requesting 1 gig of memory displayed over here. Then we see a bigger job that's using up 8 gigs of memory, 8 cores, and is lasting 6 hours. And then we see this 2 hour job that's requesting 9 gigs of memory, so almost all of the memory on the system. Now, even though this is a serial job and there are cores available before, we see that there's not enough memory for this job to run at the same time as this one. And this is an important aspect in understanding how jobs are actually charged, which we'll see on the next slide. And then we see a typical multitask job that's using 10 cores and relatively little memory per process. It takes up this whole node, but not all of the memory. So these different job sizes or footprints affect how long it will take for resources to become available for these to run. So making jobs easy to fit on a node affects the wait time. Another thing, though, is that the billing of these jobs is not only the number of cores that they're using. In the case where a job is using 1 core and 1 gig of memory, in this case, the billing is 1 core equivalent. In the case where a job is requesting 8 cores and 8 gigs, in this case, the core equivalent is then 8 core equivalents. Now, there's also a parallel job that's happening across nodes. So this 10-core job has 2 cores on this node, and then has cores on other nodes, and it's not requesting much memory, so it's being charged 10 equivalents. Now, the difference that we see is in this serial job, it's requesting 1 core, but 9 gigs of memory. This job is being charged 9 core equivalents. That is, it's using the amount of memory that's the equivalent to 9 cores. It's basically using up memory that's also isolating the equivalent of 9 cores. So importantly, this is how jobs are charged on the system. Now, it depends on the system. On the Cedar and Graham systems, the core equivalent is basically 4 gigs per core. And then this last 10-core job, although it's not using up all of the memory, it's still being charged 10 cores because it's taking up all 10 cores. So understanding the billing of this affects how the jobs that you're submitting might be affecting the wait time of your subsequent jobs. This is something we'll touch on more later. Now, in that example, we basically talk about jobs coming in and then being scheduled in the order that they come in, but this isn't really the case. The jobs are reordered based on their priority, and a job's priority is recalculated all of the time. So let's say there are now 10 accounts, A1 through A10, and all of these accounts submit 1 job during the first scheduling cycle. So all 10 accounts have equal shares on the system, so they basically have a target of 1 core usage over time. If they all submit a job, they get basically first in, first out, and their fair share is equal, is 0.5. Now, if on the second scheduling cycle, the account 1 and account 2 each submit 2 jobs, then they get 2 jobs running here, and this will affect their usage on subsequent scheduling cycles, as this increased usage drives their fair share down. Making the fair share of account 1 and account 2 go down below the other accounts means that the jobs coming from that account will have a priority that's smaller. And jobs in the queue are constantly sorted by their priority for consideration by the scheduling cycle. This is how usage is tried to be shared equally across accounts by the scheduler. Now, on the systems, these fair share targets are not completely equally divided across all the users. So in production, target shares are not equal. There's resource allocations, so the resources for research groups and the research portals and platforms are defined by unique shares. So this is research groups can apply for a certain target usage for the year. And then the rapid access, or basically default usage, is the equal shared residual system resources available beyond the allocation. So in actuality, rather than all accounts having equal shares of one core in this example, we have our resources for research group that has a 2-core target, for example, another one that has a 3-core target, et cetera, and then the default usage is basically what's left over after all of the allocations are accounted for, and that's divided among the default accounts. What we've talked about so far is basically the node, so the resources on a node and the resource requests that are the shape of the jobs you want to run. Now we want to look at how those nodes are organized into the cluster. So if we take this one node and then we put it in one little box, then all of these boxes make up the cluster. So the partitions restrict jobs of specific shapes to node sets or subsets of nodes. Full node jobs can run on most any node. So if you're requesting all of the cores on a node or all of the memory, then that job being isolated to or having the only usage on that node is favored in some ways by the scheduler. Jobs that are 24 hours and shorter can run on most any nodes. Longer runtime jobs have access to fewer nodes, and partial nodes, or by core, have access to fewer nodes. There's another type of partition called a backfill. And this is basically if nodes are left idle by other partitions, then short-running jobs that are high enough in priority can run on those nodes. So what we end up having are these different subsets of partitions, where different nodes belong to a partition, and jobs based on their resource requests get access to those nodes. For example, what we see here is if you're running jobs that are requesting 28 days, you get access to a very small subset of nodes. So this is very important in that not only is a 28-day job difficult to fit in the scheduler, for example, but it has access to very few resources to run. Another thing is that if you're running jobs without requesting the entire node, then those by core definition jobs can only run on a subset of the total nodes in the system. Now, if you're running short runtime jobs at this point, within a day, those get access to the entire system, but only if the nodes are otherwise idle. So this increases the usage of the total system. Now, here we see just a brief example and review of what a by node versus a by core job looks like. So this blue job is running by node, so it's taking up the entire node. It can run out here on this node and in here on this node, but a task that's distributed across nodes, for example, a few cores on this node, a few cores on this node, and a few cores on this node, although that can take advantage of gaps in the system and fill out the utilization, these jobs are isolated inside the nodes of the bi-core partition. Given these aspects of basically the nodes in the system, how the scheduling happens and how priority is organized, and how the nodes are organized in terms of subsets and partitions, what we want to do is be able to understand how are the systems actually currently configured to best satisfy the workload that's on the system. So monitoring jobs, the queue, and the cluster. So one thing that we might want to be able to do is show all of the jobs in the queue sorted by their current priority. Now, to do that, we can use the sq command, and we can sort it by priority, and then we can organize the output, showing the accounts and the priority, which partition they're in, and then we can sort of manage the width of the columns and show the cores and the memory and the submission time, etc. And then we can plot that and basically see where a certain job is fitting in terms of its ordering in the queue and the ordering that the cluster is actually considering these jobs in. Now we might want to also just show the properties of all of the jobs on the system since stated date. So looking at your own jobs in the past and all of the jobs on the system in the past can be accessed with the sact command. In this case, we're basically the -a. We're going to be showing all of the jobs, not just a specific user or my own by default. And then the x basically just shows the main step of the job. And then we can show it since a certain time. We can also show it up to a certain time and then just look at specific intervals that we're interested in finding. Now, we can organize the output of these columns, and we'll go over examples of this in the command line in a minute. But we can show the account, so basically the first 4 characters of the account, which will tell us whether it was an allocation account that did it or a default account, the partition that it ended up in, the submit times, the time, the memory that's requested, the number of CPUs, the nodes, and then the state that it's in. And then we can look at that as a summary. Now in the command line, this will basically just print out one line for all of the jobs that we want to summarize, and we can look over it that way. But in this webinar, what I want to do is basically use this command as an example of redirecting this to a CSV, and then using local tools on my computer to summarize and plot that more intuitively. Now, for understanding the node memory gaps and things like this that we want to consider whenever we're submitting jobs, we can check information about the nodes by using the sinfo command with the -- node and long, and this will tell us the actual memory limits of nodes, and this will list them all. And then for describing partitions, there is a summary script available on the systems called partition stats. This basically summarizes all of the nodes on a system like Cedar and Graham. Shows us how many nodes are in each partition, how many jobs of those partitions are queued, how many are running, etc. So we'll go over that example. And a lot of this is taken from examining the scontrol show partition command, which gives you the exact properties of the partitioning of the system, which we can look at the details once we log in. Now, what I want to talk about today is really getting at visualizing what it looks like over time to have jobs running on these systems. And what the load on the system looks like relative to the throughput and how that's managed basically by wait times. So what I have here, and we'll run an example of this in the command line, is a call to sact, where we're listing all of the jobs, and we're just depicting them between a specific time. So any jobs that were in any state from October 4th to October 5th at time 0. And then we're going to delimit it with the line. And then we're going to specify the memory in megs. And then we're going to list all of these outputs. So we're going to get the job ID, we can get the user and the accounts, the number of CPUs, the nodes, et cetera, et cetera, et cetera. And then we're just going to reduce it down by piping into grep or different tools. We basically just want anything that's in a CPU base partition, and then anything that is one of the allocation groups. And then we're going to redirect it into a CSV file. Now, what we do locally once we generate these in the cluster is we just mount the drive where we're generating them, and then we start up some local application. In this case, I'm using Octave, which would probably translate well to MATLAB. And I'm going through each one of those jobs, and rather than trying to look at the state of those jobs in a table, I'm plotting each job as a sequence of gray and green lines, where the gray line, so in this case the x-axis is time in hours, the gray line represents the amount of time a job waited, the green triangle represents the start time of the job, and then the red triangle represents the end time of the job. Now this is all of the jobs on the Cedar system between midnight or 0 on October 4th and October 5th. The y-axis in this plot, going up this way, represents basically the resources being stacked one on top of another. So in this plot, no job shares any point on the y-axis. All the jobs are just stacked up. And the height of the job represents how much that job was charged. And we'll take a closer look at this whenever we do the demonstration. But what we can get from this is now we can plot down here the actual resources in demand in the queue. So this gray line represents the cumulative resources in the queue at every time point. And then the green line represents the utilization. And what we see in these plots are basically the utilization is meant to be a horizontal line in the interval between these vertical lines when we're querying those jobs. So regardless of how much demand in the system there is by this subset of accounts and partitions, the actual usage, or the green line, is meant to stay horizontal. That's basically the accumulation of these accounts on the system is staying at its target. Now it's allowed to go above and below it and oscillate around it. But this is basically the way of summarizing the throughput or accounts staying at their target versus the amount of demand in the queue. Now what we see over here is a summary of a system for a month, where between these vertical lines we get the actual usage of the resource allocation groups altogether versus the default or unallocated groups altogether. And this is where we see that although the usage of these account groups are allowed to spike and go above and below, there's clearly a target usage of these systems. The dim lines are the actual load on the system by these account groups. So regardless of the load as it varies over time, the throughput is what stays constant at the target of those accounts. So we'll take a look right now at actually generating some of these plots. I've shared a GitLab repository that has these sact plot functions where we can go into the system and then we can just generate these and then take a closer look at them interactively. Now, I'm just going to give an example of doing it with this one command, the sact, so summarizing the table that we get, and then using Octave locally to visualize and interact with the data. So the first thing that I'm going to do, I'll have my notes here. And then what I'm going to do is I'm actually going to log into Cedar. So I'm going to do SSH, Dazard, Cedar. And then while I'm in here, I'll run a couple of the summary commands just so that we see what they are in terms of time. Okay, so here I am, I'm logged into Cedar. And what I'm going to do is I'm just going to run a couple of commands. So the first one that we talked about is actually showing the queue and sorting it by the priority of the job, and then listing a few of the aspects of it. So here we have basically each line is a job. The very last column is the priority of that job. So by using this, what you can do is you can see where your jobs are ending up in the queue. And this is the order by which the scheduler is considering them for dispatching to compute. Next thing that we can do is we can actually show properties of all of the jobs basically since October 8th. And then we can list a bunch of different properties. The properties that we list are several, and we can check the man sact to see which properties we can show. We can also get things like the actual memory consumed by jobs using this command. So here we see basically each line again is a job. We see for completed jobs which partition dispatch the job, its submit time, start time, and then the time limit that are requested, including the requested memory, et cetera, et cetera. Then we'll show a couple things about the actual system. So a quick look at sinfo, and what we want to do is find properties of the nodes. This will list all of the nodes for us, and in particular we want to see what the memory limit is on these nodes. The memory limits of the nodes are also available in the documentation, which we can show quickly. And importantly, the memory is not necessarily the same if we specify it in terms of gigs or megs. So base memory nodes have available to run jobs 128,000 megs. Now this, if we specify 128 gigs for a job, that will actually be requesting too much memory, and those jobs will not be able to run on the base memory nodes, instead be restricted to smaller memory nodes, which can dramatically increase the wait time of those jobs. Other thing is we can take a look at the partition stats. Partition stats is a way of summarizing both calls to the node properties and the partition properties, as well as which jobs are queued and running on the system. So by calling partition stats on any of the system, we get a layout of the resources as well as the jobs. So in this case, the partitions are organized by running in 3 hours, 12 hours, 24, 72, 1 week, or 1 month. And then the colon separating each of these values represents whether it's a binode partition that's expecting jobs to be isolating themselves and taking up exclusive access to the node or by core. And what we see here is the number of queued jobs by those partitions, by regular memory, large memory, GPU or GPU large, the number of running jobs, the number of idle nodes, and then the total number of nodes, so basically all of the resources. This can be called at any time to get a snapshot of the current state of the system in terms of how the nodes and the partitions are being populated. Now, what I want to do next is actually take some of this tabular data and then just, instead of trying to look at it in the terminal, create a CSV file and then use local tools to summarize and plot it. So what I'm going to do is I'm going to go to a little folder I have here called the qplot, and then I'm just going to list a bunch of files I've generated. So we can see here, this is a folder that I use to summarize different parts of the system when it's running. Now in here, what I can do is I can generate one of these account calls where I want to get all of the jobs between October 9th at time 0 and the 10th. So basically describe all of the jobs from yesterday, just the CPU base of the allocation groups, and then redirect it into the CSV file. So I'll hit OK. That will take a couple minutes, and then we'll see that this one generated probably right here. Okay. Now that I've generated this file, I'm actually going to log out of the system, and here I am in my local computer in this qplots folder. And what I'm going to do is I'm going to list the contents of my temporary mount folder, which is empty. And then what I'm going to do is I'm just going to mount the folder on Cedar into that directory so that I can access those CSV files locally. And once this connects, then what I'll do is I'll open a local instance of a program and then start working with it. So now if I test the temporary mount, I see that I have access to the CSV that I generated. Now on my local computer, I can open a tool. So in this case, I have Octave. I can go to qplot. Then I can look in temp mount, and I can see that my files are there. Now, this is basically just demonstrating on one of the tools that I'm comfortable with. Of course, you can use this in anything that will read a CSV. And what I'm going to do is I'm just going to load a package that will read in the CSV files. And then I'm going to add the path to the tools that I've made available for running or plotting these resources. And then while I run this, we'll go take a look at them. So here's the command that I'm going to run. I've pasted it in here. What this will do is it will give me a couple outputs of the load on the system. So the tally of the running jobs and the tally of the queued jobs at the timestamps by running the job stack command. And the job stack command basically takes the input of a file name, the CSV, and then just an indication of which columns represent what, and then the actual time interval. That was queried in the sact call. Now, while that's running, we can go over to the actual sact-plot GitLab, and then we can take a look. And what's basically happening here is these are just M files for MATLAB or Octave, and this function takes the inputs of the CSV file and then parses them so that we have the different variables like the submit time, the start time, the end time, etc. And then it just walks through all of the jobs here, identifies what state it's in, and then basically builds the lines to be plotted in that array. Once it walks through all of the jobs, getting all that stuff, then it just generates the plots that are listed down here at the bottom. Now, once those plots are generated, we get two that represent the usage during the interval that we were looking at. I'll maximize this one. And then taking this, we can then zoom in on certain aspects of it. And then here we get a better look at what it means to be stacking these jobs. So each one of these lines represents a single job. This job, this vertical line, represents the duration that a job ran in hours listed down here, and the height represents the core equivalents that were consumed during that job. The gray line of any job represents the amount of time that it waited. And if we take a closer look at any of these, what we can see oftentimes are what it looks like to have a set of let's say, a sequence or a serial farm of jobs. In this case, right here, we have a very good example where this represents a lot of jobs that were submitted at once, but the actual runtime of the jobs is a diagonal line. And this is basically demonstrating that the wait time of the serial farm is what keeps an account at its target share. So the wait times up here for this series of jobs are long because the scheduler was trying to keep that set of jobs on the trajectory of its target. Once we have access to all of these things, you can find other documentation and getting help, particularly that's the Slurm scheduling system. So getting access to these commands like sinfo and scontrol and sact are documented here. Compute Canada has specific wikis for understanding the scheduler, so you can find properties of the general purpose systems at the wiki Graham and Cedar. You can find details for running jobs, where many of these properties are described. And then you can also find information about the job scheduling policies. There are also other related videos at Sharcnet that describe different ways of submitting jobs. So sort of a precursor to this presentation is the video called All About Wait Times in the Graham Queue. There's also one on serial farming on Graham, and this goes over scripts for submitting serial farms so that they can take advantage of some of the properties of the system. And then there's benefits of Glost for many jobs, which was actually the last seminar, that looks at a tool for packaging several serial jobs together into one larger job. So really, once we can see all these properties, what can actually be done about wait times? So we want to consider node memory limits. So consider that the node and partition memory constraints as they relate to the resources that are available for a job. So a very simple default behavior that can be changed is request memory in megs instead of gigs. And this specific problem is, there are substantially more nodes that have 128 gigs total than other large memory nodes. But if a job requests 128 gigs rather than 128,000 megs, it's requesting more resources than are available to running jobs, and will have to then be run by a large memory node, of which there are substantially fewer. This will have a large effect on the wait time of those jobs. So understanding the real limits available in the different types of nodes and how many of those nodes are available should determine subtle differences in the memory that you're requesting. Because subtle differences like the difference between 128 gig request versus 128,000 megs can have a substantial impact on your wait time. Partition constraints. So consider how the shape of a resource request may isolate the job to a subset of resources. So the memory request that we described earlier is if you request too much memory for a certain partition, then a job gets sent to a partition that has larger memory nodes and has a smaller subset of resources in it. The same thing is true for the by node and the by core jobs. These systems are partitioned so that all of the resources are inside of by node partitions. So if you're running a job that is exclusively using a node, it's using entire nodes, you have access to more resources. If you're doing serial farming, running a bunch of very small jobs for short periods of time, there's a large benefit to bundling all of those jobs into a single job that is using exclusive use of a node. So rather than the scheduler having to try and fit it across different nodes, if you submit the job as, and this is what Gloss does, is you submit all of those jobs within one job and then request that it takes up a full node. That sort of footprint is better served by the system in the current scheduling environment. So another aspect is that heterogeneous job submissions from a single account can have substantial effects on the wait time of a job. So we talked about how different job shapes are more difficult to schedule than others. So a very small amount of memory, short runtime job can fit into a lot of places on the system just in terms of backfilling, filling in gaps. Whereas a very large memory GPU job is competing for very few resources and might have to wait quite a while before it can run. The issue here is that if a research group under one account is running both types of jobs, the wait time of a difficult to run job doesn't necessarily increase the priority of that job. In this case, if the account is doing a lot of usage of very easy to schedule jobs, while the difficult to schedule job is sitting in the queue, the priority of that difficult to schedule job will actually continue to go down, and it will get harder and harder for it to run. And that job can stay in the queue indefinitely. Now, if the research group has to be submitting both of these types of jobs, what we recommend at this point is doing these two different types of works on different systems. For example, doing your serial farming on Graham and then doing your GPU use on Cedar. There may be other options for this in terms of dividing accounts into specific use, and always feel free to submit a ticket request. And then always consider the core equivalent usage charge. If you are submitting several jobs, and let's say they vary in terms of requiring 3 or 4 gigs of memory, but you decide to be safe and submit everything with 8 gig memory requests. Regardless of what those jobs actually use, your account is charged for the memory that you've reserved. So if you have a large serial farm of jobs that are using 3 to 4 gigs, but you're always reserving 8 gigs, each one of those jobs will be charged double what it needs to be. And by being charged double what it needs to be, your throughput over the time will be half of what it could be. And this, of course, will express itself in larger wait times, where the account is being throttled by the fair share. So what else can be done? So the job resource throughput. This is always the case, regardless of how the system is configured. So decreasing the job throughput, minimize accurate requests, do checkpointing. So if you're running very large jobs, very long runtime jobs, the amount of resources those can run on is diminished. So making jobs run in a shorter amount of time is beneficial. And even if the job has to run for a long time, what you can do is break it up into checkpointing pieces, and then use dependent queuing so that the job runs nicely in sequence. And then consider compressed versus distributed footprint of MPI jobs, but also of serial farming jobs, bundling them all together into the exclusive use of nodes. So understanding the load on the system. Now, users have no control over the load on the system, but there are methods of understanding it and visualizing where the load of certain properties might be worse than others. Now, there's also a method of changing what resources are available, and that comes in the form of the contributed model. This gives researchers an avenue for actually contributing nodes to the system and then getting specialized targets or access based on the contribution of the resource. And then always consider the effect that the jobs you're running have on your fair share or the priority of the subsequent jobs. So be efficient about usage, both in terms of the number of jobs and the footprint that you're running, as each job has an effect on the priority and consequently the wait times of subsequent jobs. And then if the default usage isn't sufficient, you aren't getting the throughput that you require, and you need more than 50 core year equivalents over a year, we recommend to apply for a resource allocation where you justify a target usage that you require, and then it's reviewed. So in conclusion, the scheduling policy prioritizes account target consumption, but also just prioritize the total utilization and efficiency of the system. Whenever submitting jobs, you should prioritize the optimal running of the procedure. So the job should be running with high performance that you determine through profiling and scaling tests. But also consider that the shape or the footprint is feasible within the scheduling policy. Now the configuration of the cluster, the way that the partitions are distributed is adjusted by the national scheduling team to best suit the workload defined by the user. So on our end, we monitor the workloads in the system and try to build the distribution of the partitions to best suit that workload. As always, do not hesitate to open support tickets regarding how jobs should be submitted or what load is on the system. These discussions are valuable both for researchers and staff trying to optimize the system. So you can just email us at support@computecanada.ca. Thank you for your attention.